Hello everyone, welcome to the next joint meeting of Washington Quantum Computing Meetup and the Warsaw Quantum Computing Group. Today our speaker is Sumit K. She's an intern at Q&Co in Amsterdam. Hello Sumit, it's a pleasure and it's very great to have you with us. And the title of the lecture is Quantum Simulations of Many-Body Effects in Isoelectronic Systems. So this meeting is recorded. If you have any questions to our speaker, please post your questions on our chat, and we'll ask questions at the end during the Q&A session. And before we start, we would like to announce that there will be another meeting of Washington Quantum Computing Meetup on Monday, on 24th of May. The title of the talk is Arithmetic Circuits for Quantum Computing. So I think we can start. So Sumit, welcome once again, and the Zoom is yours. So I will just stop sharing my screen now.
Thank you, Paolo. Hello everyone, I'm Sumit, and currently I'm working as an intern at Q&Co, Amsterdam, and I also recently started working with the Center for Quantum Engineering Research and Education, Qiskit, in India. So we do quantum chemistry with quantum computers, or we use simulations. We make simulators like a quantum simulation of many-body effects of electronic structure problem and so on. So today I'm going to present one of our papers that we recently submitted to a peer review journal, and it's already on archive. So I'll discuss that paper with you. So it's on quantum simulations of many-body effects in isoelectronic systems. So this is the title of the paper, and it's on archive. So these are the following authors. So we all are working in the same institute, and this work is not explicitly done with Q&Co, but there are other works that we are doing there. So this work includes work mostly at the Physical Research Laboratory in India. So this is the archive number for your reference. So the outline of my talk goes like, first we'll discuss the overview of the current status of quantum computing applied to quantum chemistry, where the field stands in the present day. Then we discuss the work we've done in this paper, that's calculating the ground state energy of an atoms or ion, more specifically the isoelectronic system which we consider, that I'll talk about later. And we use the variational quantum eigensolver algorithm that will discuss in detail how it works and how we can perform quantum chemistry calculations on a quantum computer using this algorithm. Further on, we discuss the various submodules of the VQA algorithm. The VQA is this variational quantum eigensolver. So there are different submodules like Fabian to qubit mapping, there is optimization, and the number of measurements and so on that we'll discuss. So next we discuss the results, what we got, the conclusion followed by future plans of our group. So when we talk about the present day contributions being made in the field of quantum chemistry with the use of quantum computers or simulators, so mostly people are doing atomic and molecular calculations. So there are some works that discuss the applications in material science as well, but just like the work I'm currently doing at Q&Co, so that deals with material science. But most of the existing literature is on molecular calculations. Rather, I would say that about all of it is on molecular calculations, but we for the first time have tried with the atomic systems or singly charged ions. So currently the electronic structure theory of atoms and molecules can be dealt in two different ways, because earlier it was the only path available, that is classical computation. So the classical computation for electronic structure problem takes around exponential time, and but we have well developed tools and techniques by now. So it's like we have the couple cluster theory or the full configuration interaction. Like there are many theories that can help us solve the electronic structure problem on classical computers. But now the open paths we have is quantum computation. With the advent of quantum computers, we have exponential speed up, saying that the computations take polynomial time. So it's a relatively new field, so people are working and making new discoveries every day, I would say. So there are many algorithms that people use in quantum computation in order to deal with the electronic structure problem. So one of them being phase estimation. It's quantum phase estimation. It uses the classical and quantum hybrid approach. Similarly, is this variational quantum eigensolver, which will focus in this talk, and another is quantum annealing. So the field stands at this position here, where we have all the algorithms, and we are trying to prove the quantum advantage and trying to leverage that advantage to perform the calculations on a quantum computer, the electronic structure problem on a quantum computer. So this is all about the current status, and I have some references for you that you can see that these are the um, few papers that make use of the variational eigenvalue solver, or the variational quantum eigensolver, like this VQE algorithm and many other algorithms, and perform quantum chemistry calculations on a quantum computer. So one of them, this is a very old and good paper by uh, Alberto Caruso, and you can have a look at the others if you are interested later on. So now we'll talk about the variational quantum eigensolver algorithm. So I say that we use the VQE algorithm in our calculations. So what VQE means is actually, it's called a variational quantum eigensolver. It means that it has a classical as well as a quantum approach. So it's a quantum classical hybrid algorithm. So the components, some components are classical, whereas others are quantum in nature. That means that half the things will be solved on a classical computer, and other half will be solved on a quantum computer, or you can say likewise a quantum simulator also. So this is well suited for the noisy intermediate scale quantum era. That's the NISQ era. In this era, we have like 10 to 100 qubits at most. I mean, now IBM has announced which is a Condor machine. It will have a lot many more qubits, but in this present era, this is all we have, and this is what we. Uh, yeah, okay. Someone said that I'll share the link on the chat here. So, so as the name suggests for the VQE, so it uses what the VQE algorithm. It uses the variational principle to obtain the ground state energy of the quantum many-body system. So, what the variational principle in quantum mechanics is that we get the minimal. You can say the energy obtained is variational in the sense that the lowest eigenvalue is the ground state energy. So we have this expression for energy. Now here when we talk about variational principle, you see that the unitary operation here is parameterized. So this is the main crux of the VQA algorithm. So we parameterize any ansatz here. U can be called a unitary operator or ansatz. So this needs to be parameterized, and then this theta has to be minimized further on, so that we reach a minimum energy. So this we can say is the psi state we're taking u theta phi naught. So here u theta is the unitary operator that is parameterized by set theta, and this is called the reference state. So a reference state here, mostly what we use in our calculations is a Hartree-Fock state. They can be, you can also start with the zero reference state, but we use mostly the Hartree-Fock state because it becomes easier for the optimizer to reach the optimal or the minimum energy value. Yeah, I will discuss everything in detail further on. I mean, it looks very superficial for now. So EGS here is the ground state energy of the system. So the equation here tells us that the energy obtained is variational and is an upper bound to the two ground state energy. This is of course, the variational principle, and this algorithm makes use of the same. So in principle, we can also calculate other properties, since one obtains not only the energy but also the wave function. So once we have the wave function, we can easily calculate and compute any property on a quantum computer or classical quantum hybrid approach. So, so any property can be expressed in this form. So our goal here is to find the ground state energy of the many body system, and we choose the atoms like the isoelectronic system to test for the various factors that go into such calculation. So now the algorithm itself, what does it do? So we have the Hartree-Fock equations which are solved, and one electron and two electron integrals are generated on a classical computer. And once these integrals are computed from a classical computer, they are fed into the inputs onto a quantum computer, which basically solves this equation for the set of initial guess parameters theta naught. So this becomes clear if we go further in the talk. But the idea here is that we have some classical coefficients that we get from the solving the Hartree-Fock equations, and then we need to uh, use them in the our computation so that we get the total expression for the energy. So then further on, what we have to use is the unitary operators that depends on some parameter theta. So these are the guess parameters we can say. So talking about the Hartree-Fock state, just this state, if we talk about only this state, so this can be written in the form of orbitals. So when we talk about atoms or electron, like when we talk of atoms, we have orbitals. So this notation you might be very familiar with. So this can be written. This has to be represented as qubits if you want to talk about quantum computation. So this, how it gets converted to this is the major question here. So how do we do that? So there are many ways to do it. Like one of the approaches is where we use the occupancy number basis, or we use this simple notations for this as 1 tensor 1, which are the occupied orbitals, and 0 for the unoccupied or the virtual orbitals. So this is one of the reference states that can help us retrieve the ground state energy. So so when so this was the first step. We can say we talked about only the this part. Now coming to the rest of it. So I thought that we use some inputs from the classical computer, like one electron and two electron integrals that are fed into the quantum computer to calculate the energy. So what that means is we have the Hamiltonian in the second quantized form that can be written in this form. So we usually work with the second quantization uh, for the quantum computation, because these operators, the creation annihilation operators, can be easily put as poly matrices, and poly matrices can be easily written as quantum gates. Yeah, you might be familiar with XYZ gates. So these can be converted to XYZ gates, and hence we can perform this computation on a quantum computer. So these sets of one electron and two electron integrals, they are fed in from the classical computer, and hence the you can say the algorithm is called the classical quantum hybrid, because these are fed in from the classical computer. These are not computed on a quantum computer. So these also will be converted to XYZ gates when we want to do make a circuit and run on a quantum computer. So the energy thus obtained by using the simple energy eigenvalue equation will be sent to a classical computer, and the new set of parameters are determined, which are sent back to the previous step as input. So the corresponding energy is evaluated with these parameters on the quantum computer, and the process is repeated till the energy is minimized. So this becomes very clear if we follow this diagram. Um, so now you see the VQE algorithm. This is the entire diagram how VQE algorithm can be used to compute the ground state energy. So now you see it has two parts. It has the classical computer part, it has the quantum computer part, and again classical computer. So this is how it becomes hybrid. So you have the Hartree-Fock and the generation of one electron and two electron integrals from a classical computer. Then you have the ansatz for the wave function that is prepared. The parameterized ansatz or the parameterized unitary is formed on a classical computer. Then these are fed into the total Hamiltonian you can say Hamiltonian expression. So here, when these are fed in, then there's some mapping that takes place. So what mapping does is it converts the AA daggers, that is creation annihilation operators, to Pauli operators. So after this step, you finally have a Hamiltonian that has the classical inputs from here, that has a parameterized unitary, and also the creation annihilation operators that are converted to XYZ gates. So finally it's ready to be fed into a quantum computer because we have all the elements needed. So on a quantum computer, so this is how we evaluated, because we have a psi as a function of some theta. So this operator we call ta, the final expression. So this is measured on a quantum computer, and further on, when we calculate the energy, so after a classical adder adds all the small components of the Hamiltonian. So this is not very straightforward, you can say. So the Hamiltonian has a long string of x, y, z gates. So this is the Hamiltonian when we operate on the when we have the final expression. It breaks it down into small parts, and then the classical adder adds those small parts to give us the final energy. So what it does is the following. Once it measures the energy, so this is fed in, like we have the total energy with us, and the classical optimizer sees that if this is the minimal energy or not. So it keeps on looking at it, and it keeps on updating the parameter theta again and again till it reaches a minimum energy, which is our desired ground state energy in this case. So so the algorithm works in a very simple way that we have a parameterized unitary, and this thetas keep on getting updated until the energy minimum is reached. So this is just as simple, and when you put it into simple words. So other like energy calculation that involves a lot many steps that we'll discuss further. Like there are many factors on which the accuracy or the precision of the energy depends. So coming to the Hartree-Fock and generation of integrals, we'll start discussing each of the modules of the VQE algorithm one by one. So we solve the Hartree-Fock equations and generate one electron, two electron integrals by some suitable atomic or molecular code. Like for our calculations, we use the PySCF code to calculate the one electron, two electron integrals, and then we put everything in the codes given by Qiskit to run the simulations on two different backends. So that we'll discuss later. So these computations are performed on a classical computer because this uses the PySCF driver of, like, it's a Python-based library. So once they are computed, they'll be fed into the computation, and we can make a circuit that runs on a quantum computer. So the relevant inputs here, besides the choice of atom or molecule, are the basis sets. That is very important in what basis set we are working. So specifically, if we want to use a higher basis set that gives us a very good precision, then we have to be very careful about the qubit requirement. Since we are in the NISQ era, we have a very less number of qubits, limited number of qubits. Hence, we need to work in the smaller bases for now. Like we in our calculations have used STO3, GO60 bases, and at most used 631G. So that I'll discuss later maybe. So another step that we looked at was mapping. So I told that AA daggers, the creation annihilation operators, need to be converted to XYZ gates. So how do we do that? So in order to construct a circuit for psi xi, we need to convert the Hamiltonian and the wave function as tensor products of Pauli strings, that's XYZ gates, so that can form a circuit, so that they can be directly implemented as circuits. So this process is going over from a second quantized representation of Hamiltonian to the wave function to tensor product of Pauli strings, and it's not unique. So there are many ways to go from AA daggers to a string of XYZ gates, like the tensor product. So mainly if we name the popular mapping methods, it involves Jordan-Wigner mapping, the Bravicative mapping, and the parity mapping. So there are others also, but I won't discuss it today here. So in the so we will discuss about the Jordan-Wigner transformation here. So so other mappings, they are very time consuming, so I won't be discussing that, but I'll discuss one of the transformations that can take the fermions to the qubit basis. So let us consider an atomic orbital with these quantum numbers, and psi j represents a fermion and its occupation number is 0 or 1. As you know, the fermions have occupancy 0 or 1. So the occupancy number representation, if we take the occupancy number representation for this psi j, so it's either 0j or 1j. So again, it's a simple action of creation operator that if we act it on 0, this becomes 1, and the annihilation operator acts on 0, that becomes state 0 becomes 0. So this is a standard stuff. So when we act the creation operator on 1, this is 0, and annihilation on 1, it becomes 0. So creating and annihilating, that is just a standard how we do it. So when we talk about occupancy number basis, so the AJ dagger becomes this, and AJ, that's the annihilation operator, becomes this. So here ket 0 means this vector, and ket 1 means this vector. So for now, we were dealing with very basic stuff, and these are the basics to understand the Jordan-Wigner transformation. So in order to understand the correspondence between A dagger A and the polyspin operators, we need to consider a spin-off particle whose basis states are spin up and spin down. So we have sigma x, sigma y, sigma z as the polyspin operators. So just taking an example, when we act sigma z and spin up, so this takes an eigenvalue of 1 with spin up as the eigenfunction vector, and when we have spin down, it becomes, this takes the value -1. So we introduce spin raising and lowering operators as this. So this and this expressions plus and minus as operators. So in Jordan-Wigner transformation, so we have when you have spin plus operator acting on spin down, we get spin up, and when you have sigma minus acting on spin down, we get 0, and so on the expression you can see. So here again, what we see is that sigma spin up here can be written as this vector, and spin down can be written as this vector. So finally, you tend to see a pattern here that spin up and spin down can again be used as a basis as a qubit basis for 0 and 1, and here sigma z, sigma x, and sigma y, they are the normal Pauli matrices. So now let's introduce the new notation. We have x, y, z gates. So hence we have q plus and q minus, and q plus minus is given by x plus minus iota y by 2. So this is the final expression you can say for the Jordan-Wigner transform. So the two creation operators or the two annihilation operators AJ and AK anti-commute, but two Q minus and two Q plus operators commute. That is Qj minus and Qk minus is equals to this. So you note that xj minus iota yj, like this expression is equal to this. So we have to take care that these XYZ they anti-commute. So for that purpose, what we do is to preserve the anti-commutation, we have to apply Z operators here. Suppose A1 act like if you have to transform this to the Jordan-Wigner transform. So this acts on first qubit, this qubit index, and Q minus because it's a dagger, and others are acted upon by identity. But if we acted upon the second one, in order to preserve the anti-commutation, we acted by a Z gate on the first qubit, and so on. We keep on acting Z gates so that the anti-commutation relation is preserved. Uh, so these are the final expressions when we go from A dagger to this. So finally, we have cation annihilation operators in the form of X, Y, Z strings, because this is nothing but a string of X, Y gates. So in general, if we want to put the AI dagger, it takes this form, and AI takes this form. So uh, this is all about Jordan-Wigner mapping. Next, we come to the choice of u theta. So this is any unitary operation, as I said. But in our calculations, we can. There are many approaches that are being used in such calculations. So, like the unitary couple cluster ansatz, which we use in our calculations. There are other approaches like hardware efficient ansatz, which we can use. Um, um, that is relatively simpler, but unitary couple cluster ansatz is a theory motivated ansatz. It means that in traditional quantum chemistry, we do classical couple cluster theory, that is considered to be the uh, like if you do the CCST, that is couple cluster single doubles, that is considered as the gold standard for the chemistry calculations. So likewise, we take motivation from the classical ansatz, and then we make unitary version of it, calling the unitary couple cluster theory, which is used as an ansatz for our quantum computation. So we appropriately transform the Hamiltonian, and now what we have to convert is the u theta, that is unitary operator. Here in this case, it will be the operator for the unitary couple cluster theory, and so we have to transform the Hamiltonian that we already have done. Then the u theta, and this is to be appropriately written in the form of x y z gates, because this is possible too if it's written in the form of AA daggers. And the Hartree-Fock state, if we write it in the occupancy number basis, this too can be converted as circuits. So we discussed the circuits and extracting the ground state energy, ground state atomic energy from them. So we should take a look at the choice of u theta, which is called the variational form in literature. So you can either choose the UCC wave function or opt for hardware efficient ansatz. Again, this is a hardware motivated ansatz in a way that it is very less expensive, and it makes use of very less number of gates, or you can say the parameters are very less that are to be optimized. Whereas the precision for this is a little questionable for now, because again, it's not very expressible, this ansatz. But if we talk about expressibility, unitary couple cluster has a lot of expressibility. But at the same time, it comes with a great amount of gates and parameters. Like if I have to give an example, I would say that for a fixed number of qubits, if hardware efficient uses 1900 gates, then the unitary couple cluster will use 32,000 gates. So this orders of magnitude difference, but the precision is too very good. So the unitary couple cluster wave function is given by e to the power tau or psi naught why not? So the tau here in the couple cluster is actually just the T operators. They are called the excitation operators. But in unitary couple cluster, what we do is we take T minus T dagger. So we have the excitation operator as well as the de-excitation operator. So here T means so where T is the like T is written as T1 plus T2 plus T3 and so on up to Tn. So T1 here stands for single excitations, T2 will stand for double excitations, and so on. So all the excitations can be taken care of in this very exponent itself. But since it becomes very expensive to do all the excitations, so we stick to the CCSD approach in quantum chemistry mostly. So that means couple cluster single doubles. So that we take only singles and doubles excitations. In this case also, for our calculations, we have taken unitary couple cluster single doubles. We take on the single and the double excitations. for our purpose. So again, these T's are familiar couple cluster operators that you can check any reference on the couple cluster theory and you can understand what these T operators are. So the structure of tau ensures that e to the power tau is unitary and hence the name unitary couple cluster. So if it's unitary, it can be implemented on a quantum computer. So that was our purpose. So if it's unitary, then it can be recasted in the form of a circuit and hence it can be done on a quantum computer. So U is parameterized by some set theta, which are actually the couple cluster amplitudes. So now I've been talking about what U theta is. So theta here means the couple cluster amplitudes. These are written as theta IA. This is a single excitation, and this is the cluster amplitude. So if we talk about T1, then this is the cluster amplitude for T1. Representing the single excitation, and for T2 double excitation, this is the cluster amplitude. So these have to be tuned so that the energy becomes minimum. So the optimizer tunes these parameters and keeps on updating until we reach the optimal ground state energy. So the notations are very similar to the okay. So we have the UCC wave function now. So there is again another complication that we face in this very calculation. So in the UCCST approximation, we take tau 1 and tau 2, that is only single and double excitations. So here this needs to be, so this is not always the case. So you can write is e to the power tau 1 into e to the power tau 2 only if these commute. So if they do not commute, then you have to resort to techniques like totalization to take care of the errors that come along. So here we'll talk about the trotter error because if we have to take care of the commutation, if we have to slice it up suitably. So in order to recast such circuits, we need to slice it up, and that requires trotterization to be done. So trotterization is an extremely useful tool in that context, that e to the power tau 1 plus tau 2. If we like take the limit n to the infinity, and we can suitably slice it up as this form. So this is called Suzuki trotter decomposition, and there are many orders to which this can be sliced up. So we can say the if we say that the trotter number of 1, then this becomes e to the power tau 1 and tau 2, and there will be specific errors associated with it as well. So as higher the order of trotterization, the lower the error. So the n here is called the trotter step. Note that the above expression is only first order approximation. So there will be other orders of approximation also, and the related errors that come along with it. So we can say the trotter step of 1 will give us the maximum error that is possible, or we can say the first order will give us the maximum error. So we need to see what that error is if we want to use the trotter step of 1. So this means in a practical implementation, we need to truncate somewhere. So this introduces trotter errors in our computation, as I told. So we'll work with n equals to 1, that is e to the power tau 1 into e to the power tau 2. Now constructing the circuit for psi at psi. So once we have all the components ready, that can be totally put into a circuit, like we have the Hamiltonian converted as tensor product of XYZ gates. We have the U theta in the form of XYZ, and also we have finally the Hartree-Fock state that was already in the form of string of qubits, you can say product state. So we have the predefined rules or prescriptions for constructing the circuit for psi at psi. So this is the final form we have right now, and this can be easily made into a circuit if we like take every step and convert it conveniently. So the wave function also, and the unitary as well as the Hamiltonian. So now we already converted in using the Jordan-Wigner transformation, and we have converted the others also. Hence, a circuit can be made with this. So coming to the another part, or you can say sub-module of EQ algorithm. So there's an optimizer involved that always updates the parameter theta, that is the cluster amplitudes, and keeps on updating the energy. So it sees the energy, goes back, updates theta, then again sees the energy, and so on. So this optimizer becomes a very important part in our calculation. So so there are many type of optimizers that are available, uh, there are gradient based optimizers. Then there is steepest descent, or uh, optimizers like Cobila that make use of the simplex space. So there are these optimizers, each behaves in a very different way, but we can use any one of them. Like it is based on the problem we are using. Suppose we have a problem of minimizing the ground state energy. So we need to see which optimizer suits our needs. We in our calculations use Cobila optimizer, that is constrained optimization by linear approximation. So that is very convenient in a way that when it reaches the optimal value, it goes in a very smooth way. But if we take another optimizer called LBFGSP, that is a gradient based optimizer, that takes a stepwise, like it comes down in steps. The energy reaches in minimum in steps. So that can be a little inconsistent in a way. So we need to choose the optimizer according to the problem we have in hand. So, so I'll repeat it again that the new parameters are thus obtained and are fed back as inputs to the quantum circuit from the previous step. So once a new set of parameters are obtained, they are fed back into the circuit. Then again, the process takes place. New circuit is formed. The energy is calculated, and so on. So the process continues till we have the ground state energy, uh, or we can say the energy, or the minimum energy that actually becomes the ground state energy. So when we talk about it, we'll talk about some remarks here. So in constructing the circuit, we have five this circuit for this. We need to take care to not use of many qubits, gates or parameters as resources are limited in the current era. So, as I said, that we cannot, in principle, go to a very high basis now because we have limited number of qubits. Also, we cannot use very big systems, like big atomic systems or big molecules, uh, because of the limited number of qubits we have. So the gate also are limited because if we run simulation, then becomes a great problem because for as many as if you want to go to 20 qubits, uh, a 256 GB of RAM will be exhausted in a simulation. So on, we have to deal with the less number of qubits right now. So we also need to exploit symmetries that are present in our atomic and molecular systems and one electron into electron integrals that helps save a lot of computational time. So there are many symmetries that can be used. Like there's a mapping called parity mapping uh, that in that mapping we write the Hamiltonian and everything in a parity basis. So that has a symmetry that can reduce 2 qubits in one calculation. So since the growth is exponential, like we have 2 to the power n kind of structure. So in that way, a lot of by a factor of 4, we are saving our computational expenses. So hence symmetries have to be exploited. There are many symmetries called Z2 symmetries or this Clifford algebra and so on that can be used up to reduce computational costs. So we need to be very careful with the various aspects such as depth dependence, sensitivity of results to optimizers, and so commenting on the depth dependence. For now, if we talk about the unitary couple cluster ansatz, we use depth of only 1 here. So depth of 1. So by depth means like each layer of the circuit, how many times does it repeat itself. So if we have a hardware efficient ansatz, we need to repeat each layer a number of times so that it can cover more area on the block sphere and hence becomes more expressible. so that we can reach the optimal ground state energy. So if for UCC, but fortunately we can totally work with the depth of 1, and we don't need to go to the higher depth because it gives us the desired precision with depth of 1 itself. So so error analysis becomes an important part because there are errors from the optimizer as well. So in case we are using an optimizer and we are using less number of iterations, so that becomes a problem too, because that adds up to the error in our calculations, and hence we cannot assess the precision very accurately. So these circuits can be constructed, and the VQ algorithm can be run either on a classical computer, that is on a quantum simulation, which again is very expensive for the computers right now, and on a real quantum device that's called digital quantum computation, that involves a gate-based approach to quantum computing. So either of them can be used, a real hardware or a simulation, quantum simulation. So I'll now talk about the paper. What are the results we get in the paper and what systems we use. So giving an overview, we consider an isoelectronic system, the family for beryllium, lithium minus, and boron plus as our test system for the study of electron correlation effects that are captured by the unitary couple cluster ansatz on a quantum simulator using the variational quantum eigensolver algorithm. So here are two things that we make use of the VQE algorithm. And for the VQ algorithm, we make the use of unitary couple cluster ansatz, and we try to capture as many electron correlation effects as possible, and we test the precision of this by analyzing the various modules of such calculation. So we conduct our calculations in the following four bases. So we use the STO3G. These are the minimal bases, we can say the smallest of all. STO3G basis, STO6G, and then we go to a little larger basis as 321G and 631G. So for these systems, if we go to these, if we use these bases, then it is already reached the limit of 18 qubits. So hence, going to a very good basis like CCPV-DC would require lot many qubits, as much as 28 to 30 qubits. That is not feasible on quantum simulations for now. So we do not go to higher bases, or we would like to, but we are very short on computational resources. So we make use of two simulators provided by IBM's Qiskit platform, the state vector simulator, that gives us the results that are comparable to the theory-based ansatz. And then we have the QASM simulator, that is the mimic of an actual quantum computer. So like state vector does a simple matrix multiplication for the energy expression, whereas the QASM simulator, what it does, it forms the circuit. Then after each shot, so there are many things called shots. So after each shot, you get a measurement outcome and performs various measurements to give us the energy output. So this is probabilistic, whereas this is totally determined, the state vector simulator. So likewise, these can be compared to assess the precision of quantum computer, how well it performs. So we study the various factors that affect the precision of such calculations, such as fermion to qubit mapping techniques, like I mentioned, the Jordan-Wigner mapping, the Bragg-Titev mapping, and the Parity mapping. Then we also focus a bit on optimization, that uh, as I discussed earlier. So yeah, I'll comment a bit on it, not much. So then the number of shots, we do a rigorous analysis of number of shots that are required. That is the number of measurements we need to get the desired precision, or you can say the desired chemical accuracy for the ground state energy. And we also do some analysis for the Trotter number, what is required for the calculation to achieve the chemical accuracy. So coming to some results, what we got. So I'm giving only one atom results for only one atom in STO60 basis. So for others, if you want to see the results, you can check the reference I gave in the beginning, the archive draft. So You can see here that this gives the energy, the ground state energy, for three different fundamental qubit mappings. The JW means Jordan-Wigner transformation, PAR means parity transformation, and BK means Bragg-Kitaev transformation. So we compare our results, what we got from the quantum computer or simulator, with the classical theory-based approaches like the FCI. So FCI here means full configuration interaction. So this is the best possible energy we can get in a one given basis. So full configuration interaction, the CCST, that is the couple cluster single doubles, and UCCST on a classical computer. So this can also be performed on a classical computer using various ports. So the unitary couple cluster single doubles is represented by this line, and these two bars, they give us results from the QASM simulator. The dark blue colored is the QASM simulator result, and the state vector result is this. So this, you can see very easily that for state vector, that is the ideal, you can see matrix multiplication of the energy expression. This is very close to FCI. So if you have a perfect quantum computer, this we will achieve FCI. So this is done in the here. So we have three mappings, and for all three mappings, we get accurate results for the state vector simulator. But if we talk of QASM simulator, that is the actual mimic of a quantum computer, then here we see that the precision can only reach the UCCST, the, we can say, uh, classical UCCST like ansatz. So this is good in a way that we can actually perform UCC on a classical computer and a quantum computer, and we have some comparable accuracy. So the results are good enough, except that there's a little variation in the three mappings we use. So so this we need to take care of. Whichever suits the system, we have to use that kind of mapping. So it is said that theoretically Jordan-Wigner is to be the best, but there can be many errors that come along with the calculation when we do the QASM simulator. So here we've used 20,000 shots for 20,000 measurements for this system that that I'll discuss. Okay, I have another plot that shows it. So so by shots, I mean number of measurements. So when we calculate the energy, so as we increase the number of shots, you can see like it becomes a very beautiful curve that the number, the error here, the percentage error keeps on reducing as we go to a larger number of measurements. So more the number of measurements, lesser the error. But here we're using 512 shots. That is again one standard. Like most of the literature, we use very less number of shots to calculate the energy. But we reproduce those results, and we see that the um, error comes as a, like if we have quantum simulation, there is a high probability that the error you're getting is due to the number of measurements we use. So lesser the measurements, higher the error. As you can see, if we use 10 shots or 10 measurements, the error is as high as 17.5%. That's a lot. So if we take 5 measurements, the error is around 1% or maybe less. So uh, coming now further on, when we see that from this plot itself, that even at 512 shots we have 1% or more error. So this is not the chemical accuracy which we desire. So we go to a higher number of measurements, a higher number of shots to uh, test this, and we use the beryllium atom in the STO3G basis. So the same atom was used for the previous plot. So as we increase the number of measurements, like from 10 to the power 2 to 10 to the power 4, here we have done till 30,000. Like we start with 100 shots, and we go all the way up to 30,000 shots, and we see that the precision becomes very good. You see the error bar here. This is the error bar, and you see this becomes this is so high at 100 shots, whereas it falls down to very less when you have 25,000. So this is 25,000, this is 30,000. So this becomes apparent that as we increase the number of measurements, we get very low errors. So here also we have compared it with the classically computed energy, ground state energies. So this is the Hartree-Fock. So you can see easily that the energy here is variational. So one point why we use UCCST is because the energy is variational and we get always the ground state energy that is lower than the Hartree-Fock energy. So this is the UCCST line and this is the FCI line. So in this case, CCST and FCI are very close to each other. So at 100 shots, we could hardly uh, with this error, we could hardly make it up to Hartree-Fock state for some cases. But here it reaches, if not FCI, but reaches the CCST, UCCST accuracy at least. So we concluded from this plot that we need actually uh, like 20,000 shots at least for our calculations. So this is what we use here. So we use 20,000 shots to carry out these calculations so that the error falls from 1% for 512 measurements to 0.1%. So, or 0.00. I think 20,000 gives 0.1% error. So there are other things also, like two modules or sub-modules I mentioned. So one of them is optimization. So just comment a bit on it, that if you use like by default, if we the SciPy module of Python which we use, it takes 1,000 iterations for Cobelum. So we extended it a bit further to 2,000 iterations. So with 1,000 iterations, it gives the error of 10 to the power minus 3, the percentage fraction error. But if you go to higher number of iterations like 2,000, it gives 10 to the power minus 10 to the power minus 4. So there can be orders of magnitude lesser error if you use a higher number of iterations for some optimizer. So these errors from the optimizer need to be taken care of when we do these quantum chemistry calculations, because again 0.1 millihartree of difference also matters a lot. Then we have other thing called the Trotter step, as I talked about. So from our calculations, we saw that if we did an analysis with the beryllium in STO 3G basis, we went all the way up to 50 Trotter step, and we observed that the error remains in the range of 8 millihartree, that is around you can say 0.1%. So again, if 0.1% is according to the chemical accuracy, then we use the Trotter step of 1 for our calculations. So then we come to some conclusions. So we investigated the trends in electron correlation effects for assessing the precision with which we can determine the ground state energies of beryllium, lithium minus and boron plus isoelectronic system using the VQA algorithm. So the energies obtained using the STO3G basis showed that the state vector results the agreed well beyond the millihartree level of precision, which is again a standard accepted norm of chemical accuracy. So with respect to the best possible calculation within a single particle basis, that is the full configuration interaction method for all three systems. So for all the bases we have tested so far, like in STO3G, 6G, or 321G or 61G, state vector results are within the chemical accuracy. But QASM also we reach UCCST, but again there are many errors that need to be modulated along with the errors from the measurement number of measurements. So the results were found to be almost independent of the choice of mapping for the state vector, but we assume that they would be so for the QASM simulator as well, because there are errors emerging from other modules of the QASM simulator. So we cannot be sure if this is from the mapping difference or the other modules of the VQA algorithm. So for calculations using QASM simulator backend, we carried out an extensive analysis of the required number of shots, and with our recommended value, the results agreed to tens of millihartry with respect to the FCI method. Um, then talking about the other works and future plans of our group, uh, at QNCO in Amsterdam, so we are working with the experimental proposal for the natural fermionic simulators using the cold atoms. So we are trying to make a simulator that makes use of ultra cold physics, and it can simulate, or it can actually mimic the uh, 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 a gellium like, or gellium is actually a free electron gas. So such system can mimic that system, and can be used as simulations, and further can be used as a quantum simulator for such calculations. So yeah, I won't be talking much on this, but if you have questions, you can ask. Um, at Secure, in PCG test that I'm also interning now. So we are working with the so for this calculation, this work itself, so we extended the work, and we are working on quantum noise for quantum chemistry calculations. So whatever, so these, if we when we use quantum simulator here, we do not include quantum noise in it. So it is in ideal in one sense that it does not have any noise. So next we plan to add noise modules to it, like depolarizing error, or amplitude damping, and so on, to see, or some bit flip error kind of things, to see what quantum noise does to the calculations, and how can we control that noise, and how can we mitigate the errors emerging with that noise. So this we're working on right now, and we're also working towards building a new hardware efficient ansatz. So there's many lot of literature available in hardware efficient ansatz. Many groups have tried it, but with the failed attempts, I would say, because the precision is not very good. So we are attempting to construct an ansatz that is low in cost and has desired accuracy. So for that, we are working, collaborating with the Tokyo Institute of Technology, and we will try to build an ansatz that uh, fulfills the requirement of quantum computation on for quantum chemistry. So with that, I say thank you for the invitation, listeners. Thanks a lot.
Okay, great. Thank you, Sumit. Very
Yeah.
interesting, very nice presentation. So actually, we have some questions from our
Okay.
participants. Yeah, there was a question about link to the paper on archive, but it has been already shared. There's
Okay.
a question
Okay.
from Ioannis. Could you please repeat what code did you use for classical calculations?
Uh, yes. So for classical calculations like FCI, so in this you can see all the classical calculations here. So we use modules called PySCF. So PySCF is a Python-based library that can be used to compute the one-electron, two-electron integrals that go into such calculations, as well as the Hartree-Fock energy. So so these are from PySCF. But if we talk about CCST and FCI value, these are used with the code name Dirac. So Dirac is a quantum chemistry software that can be used to compute the such energies from using these theory-based ansatz. And for UCCSC, when we obtain it classically, we use the open fermion code. So all of these have been obtained with different software packages for our calculations.
Great, thank
I
you.
hope that answers.
Perfect. Yeah, I think this was a very, very good answer. The next question is from Nikos. I thought JW mapping was exact and saw the results precise. Is this not true?
Uh, Actually, if we talk about mapping, so when you when you say that different mappings, you cannot say that one mapping is exact and others are not. So ideally, if we talk about the energy from all three mappings, should be the same, because when we take exponential, since the exponential of the Hamiltonian is isospectral, so when we map it, it should be the energy should be same. So Jordan Wigner too, I believe in the C. It is precise. So others are also precise as well. I would say just in the difference in the qubit encodings, the difference in the structure that we see the little differences we see for the QASM simulator. But as I said, I can not say with like I cannot be firmly I cannot say it very firmly that this is the error from the mapping and not from other modules for the QASM simulator.
Mm-hmm. Okay, great, thanks. There was a question about recording, so most likely Helen will post a link to the recording on the events website. So don't worry, but please follow our website, and of course we'll also publish information on our in social media on Facebook and Twitter at least. There is a question about STO XG basis effects. So how does this STO XG basis affects the VQE efficiency?
Yes, that's a great question, I'd say. So when you have, so there are different bases I talked about. If I go to the list here, so these are bases we use. So when we say we use different bases, it means that for our uh, whatever we have in our calculation. So we will say the number of terms in the Hamiltonian, how do they scale? So these are you can say the basis function, the Gaussian orbitals. So so STO3G, STO6G, these are the minimal bases. STO3G uses three Gaussian functions. That means that it is the smallest possible. So not smallest possible, but it's one of the minimal that the basis that requires minimum number of functions to be represented. So the lesser number of functions you have, the lesser the accuracy. So the requirement for qubits will be very less. So you can easily carry out the calculations on your own laptops and all. But the precision will be lesser. Like if you go here for STO3G, I don't have the results here on the screen, but suppose this is 14 point, you can say 55.6 here. So for STO3G basis, this will be 14.4 or something. So you'd say that the experimentally obtained energy will be very far off from the obtained energy if you use a small basis. So that's all there is. So if you go to a larger basis, then the precision will be very good, but the qubit requirement will increase exponentially. Like if this is 10, this becomes 18 or 20 qubits.
Okay. All right. There is another question about the computation times for QASM simulator. Yeah, have you measured any times of computations?
Yeah, so it takes actually there's a lot of difference between the computation time for both of these backends. So since this is direct multiplication, it won't be very expensive and hence it will take very less time. But if you talk about QASM, so on a real quantum computer, you would say that the process becomes very fast. But if we talk about the simulator, the QASM simulator, so it has to measure each time. It has to update the parameters, then again measure each time, and like as I told that there are like 20,000 shots required to reach the chemical accuracy. So it has to measure 20,000 times. It has to construct the circuit and measure it. So of course it takes a lot more computational time than this. So
okay.
yeah.
Okay, great, thanks. All right. I don't see more questions on our chat, so maybe I will just ask the last question. In this method, you use VQE, you define Hamiltonian and Tron experiments using Qiskit on IBM's quantum computer. Do you think that it's maybe worth to explore applications of quantum annealing and Dewey smashing for this particular use case? I'm not sure if you are familiar with this approach, but I'm just curious because It seems to be my.
Yeah, so you're saying that for ground state energy, if we can use quantum annealing and if it's a good approach, is that your question? Yeah, quantum annealing, of course, it's an excellent approach. I would say it's way more efficient than this QE algorithm, because when we slowly evolve this state, there are chances that we don't need much of the computational resources which we require here. So quantum annealing, in fact, is one of the best approaches, you would say. So we're trying to implement it at Q&Co also in this respect, and we'll be soon out with some results.
Great, fantastic. All right. It looks like we don't have more questions, so I think we can finish for today. So, Sumit, thank you very much once again. Or maybe there's just one more question has just appeared. From Near, I assume Hamiltonian equation itself must have accommodated the need to keep changing different interatomic distances too. As we want to calculate the ground state energy with regard to different interatomic distances. Am I right?
Oh, so we're talking. Is there more to the question? Sorry.
Yes. So it was quite a long question. So you can also read it on our chat, but I can read it once again. I assume Hamiltonian equation itself must have accommodated the need to keep changing different interatomic distances too. As we want to calculate the ground state energy with regard to different interatomic distances. Am I right?
Okay. So here we're talking about we use only atoms and ions for our test systems. So we do not have the concept of interatomic distances here. But yes, the question becomes valid if we use molecular systems. So for molecular systems, we have at each like interatomic distance, we have a different Hamiltonian and hence a different energy for each of the bond length, you can say, between two different atoms. So the Hamiltonian becomes different, hence the energy becomes different, and hence the entire process becomes different. So for that, we use potential energy curves.
Great, thanks. I hope that it answers the question. But there's a good comment from Helen that we still have some time. So if anyone has any questions, you can unmute yourself and ask a question now. I can see one more question.
This is Alex.
Yeah, so Alex, go on.
Yeah, hi Sumit. Very good presentation and a lot of detail. I'm not in quantum chemistry, so my question will be very general at high level. My general understanding, and as you mentioned, there's totalization involved over here, and the VQE algorithm is also a hybrid algorithm, so you're going between the classical and the quantum computer. I'm trying to understand use cases of quantum computers and looking at chemistry. How is this path of using gate computing and using this method going to be beneficial? What do you see in the future as far as what improvements are needed to make this method show some advantage or become efficient? And as you just mentioned, annealing is much faster and more natural, I think, in solving simulation problems.
Yeah. So I would say that there's a lot of improvement required. Like ours is a pilot study in this field. So this is just a beginning of something very big and new, because at the end, what we want to prove is a quantum advantage, and we want to leverage and use that advantage. So in order to do that, we need to address questions like quantum noise that actually exist in the real hardware, because we cannot always rely on simulations. So simulations actually it has a lot many limitations, like the number of resources, like number of qubits, because again the RAM for the HPC we are using, that becomes a lot of problem, because if we cannot go to higher systems, or we cannot go to higher bases. So that if we have lesser number of noise, and we can actually perform bigger calculations on a real quantum computer. So for now, I would say the most important thing here is quantum noise that needs to be controlled, and we need to come up with more number of qubits so that we can test the accuracy that actually can be used in the industry, for material science mostly, or there are many big molecules that the industry people use for their calculations, for their experimental needs. So the process can be very fast if we have quantum computers, an advantage in that sense. So more number of qubits, more fast will be our calculations. So there's long way to go, I would say.
All
Thank
right,
you, Alex.
thank you.
Okay. I can see that we have two more questions in our chat. The first question is, I'm just curious about how result may vary for NMR system or using other, I understand, quantum computing than other quantum computer than IBM.
Yeah. That's a great question, because so as we have different physical realization of qubits or different qubit platforms, there's a lot of difference that comes with the calculation. Like IBM uses superconducting qubits, so there are other qubit realizations, like, yeah, as you mentioned, NMR. So there are many, like quantum annealing also. So the precision may vary, of course, but most of the thing that changes is the time. So the computation time varies a lot if we have different qubits, and an interesting thing is the ansatz we use. So we use the unitary theta, the u theta here. So this u theta can be recast as circuits, or any way, depending on the hardware we have. So there's something called the hardware efficient ansatz. So for superconducting qubits, suppose we have a particular arrangement for qubits. So that this u theta can easily bend itself into that kind of form of the circuit that like it exploits the qubit connectivity of that very hardware. So if for superconducting qubits, we have a hardware efficient ansatz that takes care of the connectivity. We have a best ansatz for it. So for different platforms, we will need different ansatz that can uh, perform the calculations accurately. For such calculations, I'm just talking about. So I hope that answers. If it doesn't, we cannot ask.
Yeah, I think this is a very good answer. And the next question, in recent theory, how large a molecule, in terms of the number of atoms, has been simulated on a quantum computer? So it's also another general question.
Yeah, for now, there are not many like big molecules that have been simulated. So mostly papers in the reference I mentioned in the references here. So this paper uses LIH or BEH2 at max. So not many. So at most, if you have 20 qubits or 24 qubits, like forming from the uh, two atoms or three atoms or whatever molecule you have, you can perform the calculation. So it depends on the basis and highly. So if you have STO3G bases, you can take little bigger molecules. But if you want to work in 61G bases, you'll have to work with very, very small molecules. So for now, I think lithium sulfide and beryllium hydride, lithium hydride, such molecules have been used. And biggest, I think there is not very big molecules apart from these that are being used.
Right. Great. Thanks for explanation.
I have a question. I'm sorry, I just have a question. I'm not from the field of quantum chemistry, but which I didn't. I have just a slight touch. For example, if you use some basis and some methods, like you sometimes end up with unnatural results, unphysical results, right? That's what I remember from. So by using this VQE, can you try to avoid this kind of unphysical results while you stay in a basis set? still that's not valid to use. Like, for example, I remember something like boron hydride or B6H6, and Hartree-Fock gives a garbage, and you have to go to really high different methods to get a really physical result. So, do you think it's possible with the VQE, this kind of a thing too?
Yes, yeah, this is possible, and we have got those unphysical results, to be honest. So we were testing this hardware efficient ansatz, and even with the use of the QE algorithm. So if we don't have a circuit that is expressible enough to cover the block sphere, like it does not cover the ground state wave function, then we get unphysical results, like the energy value will be higher than the Hartree-Fock energy. So then the energy does not remain variational at all. So that is possible, and that becomes a problem when we try to do something that's off the theory and more related to the hardware. I think so. So just like in Abhinav Kandala's paper here. So they do the hardware efficient ansatz. I think they are by RZ ansatz. We use a rotational Y gate and a rotational Z gate, and they get energies. I think they are very close to the Hartree-Fock. So not very good results. So you can say they just demonstrated that this is possible and this can be done. But you see, there's a total chance of getting unphysical results here also, because if you don't have a good u theta for your calculations, the ansatz, variational quantum eigensolver will not help. So there's something called expressibility. I think you can search on. So the more expressible the circuit, the better chance of getting the good energy.
I see. Thank you.
Okay.
Great.
Nice to meet Alex again. Just curious. I mean, are there any other methods of evolving a Hamiltonian in a quantum computer, like a gate computer? I know there's for optimization, there's QAOA, and then VQE is kind of a simulation. But is there no other research, or is there any other research that on gate circuits that could do an evolution, maybe in a different way or a better way?
It's not that I'm aware of this QPE, quantum phase estimation. Mostly they're quantum classical hybrid algorithms only. But if you want to talk about this ground state problem, this is all I can think of. But there are other problems, like the problems in fluid dynamics, for which they use different algorithms. I'm forgetting the name, but there's an algorithm, a very good algorithm that does calculations for fluid dynamics um, on a quantum computer. So yeah, I'm not aware of many such algorithms.
Okay, so I think they've used quantum machine learning also. I think the Q and company team also used quantum machine learning to do some PDE solutions, right? So,
yes, yeah. Quantum machine learning is really helpful.
Okay, all right, thanks.
Okay.
Okay, great. Are there any more questions? Okay, I don't see more questions on our chat. So I think we can finish for today. So Sumit, thank you once again for a really great presentation and also answering all the questions. This time we had many questions, so but it was very interesting. I believe that we learned a lot. So yeah, thank you once again. We would also like to thank our participants. I think that was a very fruitful meeting, and of course we invite you to attend our future meetings. And just to remind you that the next meeting will be on Monday, and also tomorrow there will be a meeting organized by group from North Carolina. Great, so I think we can finish. So Helen, we can stop recording, and thank you everyone once again for attending. Have a good afternoon, evening,